Martin Fleischmann thought this was at 9 o'clock, so he just barely arrived. It was 9 o'clock originally, but the talk is really scheduled now for 8:30. So I'm very pleased to have Martin Fleischmann here. 10 years ago, Martin Fleischmann and Stan Pons announced the cold fusion. They'd worked on it a number of years before. So last March was the 10th anniversary, 10 years since this subject developed. Whether you want to call it cold fusion or something else, that's up to different people. I like to call it the Fleischmann-Pons effect. That's the name I like to apply to it.
That's good.
And you don't get in trouble with that. But anyway, it's my honor to...
Kidding. You know you can't even file a patent in the U.S. Patent Office that has the word cold fusion in it?
Yeah, right, yeah.
What did I do here?
Anderson got 12 patents.
But Martin Fleischmann has won many honors. One I think that I'm impressed by in the electrochemical society is one of the top awards is the Palladium Medal Award in the electrochemical society. And his talk this morning is cold fusion, past, present, and future.
Well, I must tell you first of all that the palladium medal is still intact. We did at one stage think to do a big experiment on it, but then decided against it. Well, I think you'll see that the other speakers will tell you quite a lot about what is going on, and I've got this vast, sweeping title. But I'm actually going to take a very narrow focus, because there's only time to take a narrow focus, and I probably won't have time to do all to tell you about all the parts which I should tell you about. Now, I said cold fusion, past, present, and future, because I think it is quite interesting to see why I didn't do it, why we didn't do it for such a long time. What was behind that, and how, with the evolution of time, it became clear that there was perhaps an effect there, and that there was some sense in studying it. Because really, this phenomenon is part of a much, much wider group of phenomena. And people have looked at it in a very blinkered way. They think cold fusion, which I hate this word, these two words. This is a standalone topic. It isn't. It's part of a much wider topic. Well, for me, the whole thing starts. So I know a historical perspective is not supposed to be a good idea, but I will use a historical perspective. For me, the whole thing starts with a paper which I found at the end of 1947. I'm a very old man. A brilliant experiment by Alfred Coehn in the University of Göttingen, who took a very thin palladium wire and loaded the wire down electrolytically down here, and then applied a potential plus and minus to this wire, and measured then at different times the times of arrival of the diffusion wave at the different zigzags down the wire. Now, if it was purely diffusion, of course, you'd get a diffusion-controlled wave running this way and that way. But if, and this was the proton, because deuterium hadn't been discovered at that time yet. But if it is charged, then of course it will go faster to the negative end and slower to the positive end. And this is indeed, and this experiment is actually very important as regards the future of cold fusion. And what he found, in fact, was precisely this, that if this is the line for diffusion, then the protons moved faster to the negative end and slower to the positive end, and if the polarity was reversed, then you could make them go back to the negative end, and these go to the back to the positive end, and these to the negative end. Now, this was an extremely uncomfortable experiment, because what it showed is that the mobility of the protons fit the Nernst-Einstein equation, which you can get from this. So the hydrogen in the lattice exists as bare protons. This subject matter became totally confused later. This was just suppressed. People didn't think about this for about 20, 30 years, because it was such an uncomfortable result. And subsequently, it has been, more work was done, which is quite wrong. We can discuss this if you wish. Now, why is the easiest way to see this is to do a Born-Haber cycle on the hydrogen going into the lattice. And what we see, in fact, that the absorption of hydrogen in the lattice is exothermic. And in fact, the solvation energy of the ions in the lattice is enormous. It's about of the order of 12 eV. So the ions are extremely strongly bound in the lattice, quatern mobile. And that alone tells you that you can really only interpret this experiment if hydrogen is part of a very large quantum system, so that it can be unharmonically excited. I should have realized that at that time, but I didn't. And in fact, setting down the usual way you talk about it at that time, about the quantum mechanics of ions in lattices or anything else for that matter, we would see this oscillatory potential energy curve, and of course you could not obtain a sufficient change in the potential energy to compensate for the nuclear repulsion, except under you might in fact get some nuclear reaction under very extreme conditions. And extreme conditions I was thinking about there now would now be described as inertial confinement. But I was not aware whether inertial confinement had been discovered at that time. I still don't know, but this is what I was thinking about. And that was obviously impossible in the university environment to carry that out. Now, so I left this whole thing alone. And then in the mid-1960s, I came to realize that we really have to discuss the behavior of condensed matter in terms of quantum electrodynamics, not in terms of classical mechanics, and not in terms of quantum mechanics, but in terms of quantum electrodynamics. Now, this is an illustration. I didn't arrive at this conclusion this particular way. This is simply an illustration of the fact. And here's our good old friend in the particle theory, which calculates the self-energy of this ion in an ionic atmosphere which is static. We have a static classical model of ions in solution. But of course we know that that is wrong, that it is not so. In fact, there was a lecture here which I couldn't go to on Brownian motion, and it has been known for a long time that ions, well, Einstein did this way back, beginning of the century, that ions move by Brownian motion, the motion of ions in solution by Brownian motion. And we also know from the 19th century, the work of Kohlrausch, that they move independently of each other at infinite dilution. That all sounds all right, until you say, well, what about Maxwell's equation? They accelerate and decelerate. They have this accelerating and decelerating matter. So they have to radiate. So the only point at which the particle theory can be true is at absolute zero. It's an absolute zero theory. At any finite temperature, it is not acceptable. We accept it, but it's not acceptable. And in fact, you have to discuss the behavior of ions in solution and everything else for that matter in terms of quantum electrodynamics. The motion is rigorously quantized. There is no classical motion of ions in solution. It's all quantized. I still didn't do anything about it. But we did start work on thinking about the general problem of how we could get a handle on quantum electrodynamics. Really, I should say this, the interpretation based on this type of model is kinematic. The dynamic, the consequences of thinking about dynamics remain hidden. Now, you can say, well, why should we bother about thinking about dynamics? We are perfectly happy with kinematics. Well, that's all right, but science moves on and you come to a new frontier. You have to say, I do want to understand the dynamic properties of species in liquids. So I left this thing alone. I needed a little bit more information. And we got that at the end of the 60s, when we did some work on isotopic separation. And this work on the separation factor we were interested in finding better ways of separating hydrogen and deuterium. This work on separation factors used palladium cathodes, and you could only explain the separation factor, that is the yield, the fraction of hydrogen to deuterium in the gas phase, compared to that in the solution. You could only interpret that if the deuterons and protons in the lattice were part of a large quantum system. Now, if you take the results of Coehn and you say that really the thing is part of a very large quantum system, then you come to the conclusion that it might be possible to observe nuclear reactions at low temperature. Now, these slides which I've prepared, I haven't time to use, unless at the end we might use the discussion, we might use it. And the question we posed was simply to say, which paradigm shall we use? You know, if we understand the world in terms of models which are based on paradigms, and we have a classical mechanics, that this question is not relevant. We have quantum mechanics, and on the basis of quantum mechanics, of course, this was the conclusion I reached in 1947, there would be no effect. On the basis of quantum field theory, there could be an effect. It doesn't mean to say that there will be an effect, but there could be an effect. And incidentally, what is very interesting, the questions which we can pose from classical mechanics should really be posed in the framework of quantum field theory. And then a whole lot of new questions become answerable. Okay. So the two questions which we posed were, would the nuclear reactions of D plus compressed into a lattice be different to the reactions of D plus in a dilute plasma, and could such effects be observed? Now we said that would be yes, that would be no. But we nevertheless, although we thought that we wouldn't be able to see the effect, we started a program of work. Steinholz and I started a program of work on this topic. Now, when you decide to launch yourself on a topic like this, it's worthwhile always to check the literature, to see whether there's any evidence in the literature about that. And some of you have heard me talk this out before. This is the discovery of hot fusion by Oliphant, Hartek, and Rutherford. It's just over half a page in Nature. And I say this paper would never have seen the light of day in the tail end of the century, but this was 1934, I think, or 1933. And it did see the light of day. And here you have two deuterons reacting to form what is a triton and a proton, or helium-3 and a neutron. Now, it doesn't matter that this paper was forgotten, but what was serious about it was that deuterium was not called deuterium at the time, it was diplogen, and the deuteron was called diplon. And once you were aware of this fact, that deuterium was called something else, you can search for other papers. And this brought to light some work by Philip D. using a Wilson cloud chamber. Those of you who are as old as I am will remember what a Wilson cloud chamber is. And this work was, of course, extremely worrying. He published a paper on this also in Nature in 1934, but this is a more extended paper on the proceedings, 1933 I think it was. This is a paper in 1934 in the Proceedings of the Royal Society. And what you see, the tracks here of the proton and the track of the triton. And what is so remarkable about that photograph is that the tracks are at 180 degrees. Now they should not be at 180 degrees because the deuteron impinged on the target, which is per deutero any old thing, per deuterated compounds. It should be at 160 degrees. And lots of the tracks were at 160 degrees, but there were quite a lot of tracks at 180 degrees. And
What is Rutherford's work?
this is Philip D.
Oh, okay.
And D said, these, the evidence these reactions have been due to deuterons of the accelerated deuteron, which has lost its energy in the target, Eureka. So it was there. It's been there since 1933, actually. Only people haven't really responded to it. Okay. So we posed ourselves a series of questions, how to carry it out, how to carry this out, and because there was obviously something wrong with hot fusion, I don't know, perhaps we can have time to discuss that later. There must obviously be other reactions than reactions which are known from plasma work. Two neutrons going together to form triton and proton, or helium-3 and neutron, about equal cross-sections. There must obviously be other reactions. And interestingly enough, since the advent of this horrible topic, these reactions are now being found. You'll hear a lot about helium-4. So we posed ourselves a series of questions. How should we carry out this reaction? Our favorite technique was electrodiffusion. That was the work of Coehn. But we started on charging cathodes electrochemically. Largely, I think this was because we made a mistake, quite frankly. We were working on a mistaken hypothesis. But there are other ways you could do it. You could charge electrodes in a highly reducing medium, in a super basic medium. Obviously, we should have a look at highly oxidizing media, super acid media. This is because really the impact of a deuteron on a lattice is an extreme example of a super acid reaction. And then there are composite systems. So there are all sorts of ways you could set this thing up. And because we were trying to keep this whole thing secret, fortunately for us, we did not put neutron counters in the lab, and we did not put a tritium monitor into the lab, because we didn't want to draw attention to it. We measured the heat release. And actually, the state of knowledge in 1982 was that mercury measurements by calorimetry were certainly about as good as making any nuclear measurement. And what we used, those of you who are familiar with it, with this field, we used isoparabolic calorimeter, just a Dewar. Not initially it wasn't silvered at the top. Eventually we silvered it at the top to give us a flatter baseline for the heat transfer coefficient. And in fact, this thing is a long, narrow tube. In chemical engineering, it would be called a well-stirred tank. It's an ideal reactor. There are many sorts of calorimeter which are non-ideal. This is really an ideal system with a very high accuracy and a very high precision. If you do the analysis correctly, you can get a precision of about 1 part in 10 to the 4. If you, the accuracy is comparable, but for a long time we thought the accuracy was about 1 part in 10 to the 3. But in fact, it is about 1 part in 10 to the 4 also. So if you do that, then the sensible thing is to do some blank experiments. I found it extremely difficult to persuade people to do blank experiments because you have to, of course, find the instrument function of this device. If you make a measurement, you must know the instrument function. The easiest way to get the instrument function is to do a blank experiment. And blank experiments, this is a platinum electrode in heavy water, polarized. These intervals are actually 300 units of 300 seconds. This is the temperature time curve. This is the cell potential time curve. At this point, we impose external heating pulse to a Joule heater so we can get a calibration. And these responses in blank systems are entirely normal. And I just draw your attention to the fact that this does in fact reach a flat top. It relaxes completely, and the baseline relaxes to where it should have been. Those are sort of very simple eyeballing methods for checking that the system is reliable. but its reliability can be checked a bit more by just seeing what the thermal excess is. And in fact, the results follow a normal distribution. And for a Planck experiment, the mean rate, the mean excess rate, heat released for this particular experiment, where the input was about 2 watts, was less than 100 microwatts. So the thing is absolutely reliable. People say it isn't, but this is a lot of nonsense. So if you know now the mean rate and the standard deviation, you can look at what you get if you do the experiment with palladium in heavy water, not platinum in heavy water, palladium in heavy water. And here is some data I pulled off some Japanese results. I like using other people's results better than our own, because then at least you have some security that we haven't filled with the results. And initially you get an excess heat, which is due to the absorption. It's exothermic, the absorption of deuterium in the lattice. And then you go close to 0, and then you get a buildup of excess heat. And if you do the analysis accurately, you find that this is actually 300 sigma in terms of the performance of the instrumentation. There's no question about it. There is a build-up, a low-level build-up of excess heat, but of course you've got to be able to measure 30 milliwatts accurately in order to be sure that this is correct. Now, this being so, one has to ask oneself, why has there been such difficulty for people to reproduce the results? What's really bugging them? I mean, lots of people wanted to see it and didn't see it.
Too much of a hurry.
No. It's much more sophisticated than that. It is true. That is certainly true, but it is more sophisticated than that. And one of the things which is difficult about the system is that it is subject to positive feedback. Now, here is some more Japanese results. In the initial states of the experiment, you see everything is normal. It comes to a flat top. After you apply the calibration, it relaxes back. Okay, can everybody see that? It's quite normal, it relaxes. And then you go along and you say, well, maybe there's a buildup of heat. And then you find that it doesn't behave normally. It behaves extremely abnormally. The system does not relax in the same time scale. And after you've removed the calibration pulse, it doesn't relax to the baseline. And what in fact you see is that the application of the calibration pulse, the increase of temperature, increases the rate of excess enthalpy generation. Now, if you have a source of heat in the system which is subject to positive feedback, you cannot calibrate the system. You have to do the calibration separately. And because people haven't understood this, or have rammed it down their throats forever, they say the system's not accurate. I cannot calibrate. The system's not accurate. No, that's not true. You haven't taken into account positive feedback. Now, what is, there's something more to this story of positive feedback. Why do you get positive feedback? Why should you suddenly, when you increase, this is actually extremely fortunate, because if there were no positive feedback, we will not be able to get, if the absorption of deuterium in the lattice remained exothermic, we will not be able to get to an energy release at high temperature. But because it switches from exothermic to endothermic, we can actually get heat release at high temperatures. And this, perhaps Michael Kruger will say something about this, this switch over from exothermic absorption to endothermic absorption takes place at a certain cathode loading. And of course, if you have this move across from exothermic to endothermic absorption, you get instability. And that is the secondary reason, therefore, why we have to, the fact that we get instability means that the experiment becomes sensitive to the way you carry it out. It doesn't follow that you will always get a heat release at high temperature, because if you stay for any length of time in the region in which there is a switchover from exo to endothermic absorption, you will get oscillations, and these oscillations eventually destroy the system, so you have nothing. So you have to be aware, you have to, when you have a new problem like this, you have to cycle through the data over and over and over again. And this is one reason why it's been so slow. You have to discover this, go back, take it into account, put it into your experimental protocol, and see what happens. I must go faster. Not too fast. Well, let me just tell you that by October 1989, we've got a specific energy release of the order of 100 watts per cubic centimeter at currents of the order of 1 ampere square centimeter. That is quite heroic electrochemistry, but this is about comparable with what you get in a pressurized water reactor, so we felt justified in carrying on. And what we find, this comes up to 1992, although we had a lot of this in 1990. We find that if you go, this now is on a much smaller scale, so you can't see the fine detail. You find that if you go through the positive, the region of positive feedback, eventually the cell is driven up to boiling. And at the boiling point, we have had heat release in this region here of the order of 4 kilowatts per cubic centimeter. So normally you have about a few hundred watts. At the top you have about kilowatts. And now, of course, the cell boils dry. You can't contain such an energy release in an isoparabolic calorimeter. The cell boils dry. But there is more to this story. Because when it has boiled dry, you find that it stays hot. The cell stays hot, which Mike McCoubrey called heat after life, we call heat after death, and Giuliano Mengele in Italy, who I think has done the best work on this, calls after effect. So here the cell is dry, here it's half dry, here it's dry, and the cell here in our experiments remained hot for 3 hours. Now, this experiment, you know, we're not very proud of this experiment, it's just a fact that it stayed hot. And let me just tell you about Giuliano Mengele. Giuliano Mengele said quite rightly, well, Stan and Martin say it goes much better if you keep it hot, so I'll do the calorimetry at near 100 degrees centigrade. So the way he does this is he surrounds this cell by a thermostat set up near 90, 90 degrees, and he cools it with a stream of gas. He uses evaporative cooling to control the system, and he has a reflux to return this to the cell. And the important point about Giuliano Mengele's experiment is that it's a very well-controlled situation, and when he's got to that point, he switches the current off, he disconnects it from the power supply, and he has actually, this is published information, has had the system staying hot for 7 days. This is the excess enthalpy. There's no enthalpy input, so this is all, this shaded column is all excess enthalpy, and it's of the order of 5 watts per cubic centimeter. So what we know now is that if you do this, you can get this heat after death effect of the order of 5 watts per cubic centimeter, which is tolerably uninteresting as far as some sources are concerned. It would only be interested in certain niche applications. We know that the way we do it, we could get kilowatts per cubic centimeter. Incidentally, I should tell you that you can Melmites has a system which had 50 watts per cubic centimeter. We've had it up to 200 watts per cubic centimeter, which would give a much wider range of applications. But we were interested in trying to see whether we could maintain these boiling conditions. And to do that, you, of course, need to use a much more elaborate, not sophisticated, much more elaborate calorimeter, which allows you to maintain the conditions up here. I'll just show you one result from that. That worked ground to a halt, I'm sorry to say. What you do is you use a calorimeter, a dual calorimeter, the bottom half of which simulates the calorimeter which I have shown you. It's an isoparabolic calorimeter. And the top half is basically a distillation column. Now that is not a system with which you can do experiments with any great accuracy, but you don't need to because you get a very high energy release. So what do you see? Here's an experiment carried out in 1994. The bottom section, you see there is an excess. This is the calibration curve. Of course, when it starts to boil, you have no calibration on the bottom section. You can see an excess enthalpy release in the bottom section. Needs a little imagination to see it. But I think it's okay. And the top, much more clear in the top section, where you have a calibration curve, inputs of the order. This is the input, and the temperature difference seen. We measure that you can measure this at different stations in the top section, of the order of 70, 80 watts input, the excess of the order of 70 to 80 watts, which for this system was about a kilowatt per cubic centimeter. And this particular experiment maintained an excess enthalpy generation of about a kilowatt per cubic centimeter. The actual value of about 80 watts per kilowatt per cubic centimeter for 50 days. So we were interested in trying to begin to answer the question, can this phenomenon be maintained? So now you have certainly an indication that you can get a kilowatt per cubic centimeter. And if you're interested in the social aspects, at a kilowatt per cubic centimeter, you would be able to make a significant impact on the world's energy needs if you increase the palladium production. But that production is about 100 tons per year. It could certainly be increased, I'm told, to 1,000 tons per year. So that would be an acceptable strategy. However, having got to that point, it certainly is not sensible to continue with this particular approach because there are two sort of classes of scientists in the world. The ones who think electrochemistry is really rather interesting. They're usually non-electrochemists. And electrochemists who say, I will not touch electrochemistry. If I can do it some other way, I won't touch it. And the trick, of course, is to go to our first love, electrodiffusion, and to say, we'll do all this in a while. We'll compress the deuterium by electrodiffusion and see what we get out. And this is the part of the core program in Italy. My friends in Italy. Thank goodness we have some friends. I will leave neutrons out of consideration and just say, well, what Giuliano Preparata and his colleagues realized that is that you don't have this sinusoidal thing which you would get in the beta phase. You would eventually get a coherent system of neutrons in the lattice. It would extend. He calls this the gamma phase. Okay, let's call it the gamma phase. It's much higher probably when the deuterium goes into the tetrahedral as well as the octahedral sites. And with this type of wire approach, they have had pretty regularly heat releases of the order of 10 kilowatts per cubic centimeter. You have, of course, to use a thin wire to do that, because else the system will destroy itself. Or you have to have some structure where one dimension is much smaller than other dimensions. And on occasion, they've had 100 kilowatts per cubic centimeter. And what is interesting about those magnitudes is that they would allow one to construct, if this can be done reliably, this would allow one to construct systems which would satisfy a large proportion of the energy needs with existing production of palladium. Now, this is all low-grade heat, but a lot of the world's energy is used as low-grade heat. But increasing the quality of the heat would not be a particularly difficult problem. You could use this compression, you could add a compressor system, or you could use compressor steam, use turbo compressors. So that is about the status of the field as far as the thermal effects are concerned. But of course, there's a great deal more on particle detection, the nuclear ash, and I'll answer that and refer to that if you wish, if you have any questions on that. Thank you.
Yeah, we have time for questions if anybody has any questions. We have about 10 minutes.
Sir.
Can you say a few moments about what's been going on in detection of the primary products?
The primary products. A lot. we saw helium-4 quite early on. We had no quantitative correlation, but I think other people will talk to you about the relationship of heat release and helium-4. We had seen a little tritium. You can see tritium pretty regularly. I mean, you can see enough tritium. The work we had done originally, we would have had to have an isotopic separation factor of D to T of about 13.5, which is quite impossible. So there's no question we had generated tritium, and there are a few neutrons usually as you build it up. And many people have done neutron detection, time-of-flight neutron spectroscopy, and this sort of position-sensitive neutron detection to show that the neutrons come from a sampled area. And I like also Takahashi's work with an Ne213 scintillator, which showed quite clearly that there are some neutrons of expected energy, 2.45 MeV, but there's also a great watch of stuff out there. So, it's not the usual thing. The neutron stereo is not the usual thing. And Takahashi has gone on with this, and I think one of his most interesting results to date is that he has found a new channel, D plus D plus D, going to tritium plus helium-3. D plus D, a three-body reaction. There's not much doubt. The nuclear measurements have been done very carefully. There's not much doubt that it's a three-body reaction. Now, of course, three-body reactions, if you take stellar physics and so on, it only happens, you only have two-body reactions. Even the beryllium, what is the isotopic beryllium, which is stable long enough to give you the beta cycle? Well, there is one. It has a lifetime of about 10 to the minus 16 seconds, so you can get a sequential reaction. But this is a three-body reaction, D plus D plus D, going to P plus 3He. And these are about 4.75 MeV, the particles which come up about the same. And this has about, the cross-section of that channel is about 1/100th of the cross-section of the helium plus neutron or tritium plus proton channels. So I think there will be all sorts of, this is done at the 150 keV acceleration voltage, so it's sort of warm fusion. And I think there is not much doubt that if people if people continue to look at the products and really cover the whole energy spectrum, they will find all sorts of other outgoing channels.
But these are not really primary products, are they, of cold fusion? Because these cap rates are pretty negligible compared to the fusion event rates that produce heat.
No, they are not. They don't account for the heat. The thing which accounts for the heat is helium-4. And that's what really needs doing more and more and more. You have to really correlate, seek whether you can get a sufficient correlation between helium-4 and heat. Unfortunately, this is a very difficult experiment. And people have seen, lots of people have seen helium-4 in the lattice and in the gas. So that the status is about that there's always some tritium. There are some neutrons. The neutrons are obviously peculiar. There are always some high energy neutrons. There are some high energy tritons. There are some other channels which we should understand. I mean, we have to understand the totality of the science here. But the primary thing is helium-4. Incidentally, Mel, if I can just say, one thing I should make clear is you don't always get these effects. The materials problems are severe. The experiment is very strange. It lasts of the order of 30 to 90 days under extreme conditions. And very often, the experiment simply doesn't survive. The experiment just, the electrodes disintegrate. So that's one of the big questions behind this. Can you make this a stable system?
Going back to your original paper published in 1989, you had in one of the columns a statement, "Beware of ignition," that was associated with a 1 cubic centimeter sample, which apparently was a laboratory accident. My
It was a
question
bad
to you,
accident, yes.
is there evidence for or against the melting and the accident being due to excess heat production?
Well, this was a rather large calorimeter, and all the heavy water disappeared. Unfortunately, it happened at night, so it wasn't observed. So I don't like to talk too much about it. But the water disappeared, so it had all got to be boiled off, and then the electrode melted. It did worse than that. It sort of disappeared as well.
It was a mess.
And it was a great mess. And I think you have to say that this was exercise production. What happened after that is we were working on big samples, as you gather, you know. And I said, no, under fairly extreme conditions, I said, no, we've got to stop this. We have to work the large sheets under mild conditions and just see what we get. So we had a program of work on large sheets under mild conditions up to March 1988, when I also, there's a long history of this, but I also said that work had to stop because I could see it getting out of hand, and that we switched to using thin rods to be scaled down. See, at that stage we started to scale down so that it could never get out of control. But I don't think rods are necessarily the best things to use.
This all goes back actually in the literature. Pieces and parcels ever since Humphrey Davy, 200 years ago. And I've done a lot of this literature compilation and putting all these little pieces together. You had a laboratory over in England that you were affiliated with. Was it Harwell? Yeah. They went into experiments on this. Did they ever announce anything? I've never been able to find it in the literature.
I thought this question would come up. So I brought some slides. The Harwell said that they couldn't find any excess entropy.
Can't hear you. Speak.
Harwell said they couldn't find anything.
Oh. They had about 6 or 8 people working on it, but were they in too much of a hurry too?
6 or 8, more than that. However, when we were working in Utah, we insisted that our experiments be independently evaluated.
No.
That evaluation was not done by the original team. Eventually it was done by Wilfred Hansen at Utah State University in Logan and published, which prompted me to ask Harvard to release their data, and it's to their great credit that they released their data. So I will show you some of Harvard's results, where they compared. These are, L stands for addition of liquid, and these are all experiment cycles, okay? These are experiment cycles. This is a blank in light water. This is a calibration pulse. Here is heavy water. So if you look at this, you see suddenly a very strange phenomenon, which we've also seen ourselves, which put us, one of the things which put us on the track was that suddenly the cell temperature will decrease. Well, the cell temperature doesn't increase if there isn't a source of heat in the system. So here the cell temperature is increasing, and here the cell temperature is increasing, here it's increasing, and it goes on and on and on. Now, in fact, Harvard could never have detected the normal excess enthalpy production because the system wasn't accurate enough. But they did see these bursts here. Here is a burst. Here's another. Oh, they had all these heat bursts all over the place.
Oh.
And when you analyze, if you say there is no excess heat production, there is no excess heat production at the minima, you know, you can sort of say, okay, I don't know what your heat transfer coefficient is, but I'll say it's naught here, and then I'll see how much heat is released there in the burst. You get for the blanks, only cooling, which means we have made a very conservative estimate of the heat transfer coefficient because it only gets cooling. And for the thing when there is an actual...
So they let it die on the vine, huh?
Yeah, when you look at the real heat bursts, you see these, which is of the order of 200 milliwatts, which is about what we had in 1989. So they actually had about the same as we had.
Yeah, but they didn't have the guts to come out and say it.
Well, they had decided, they published that their system was very good, and they had seen nothing.
Uh-huh.
You know, people never retract negative statements.
Uh-huh.
The history of science is that people sometimes retract positive statements if they then feel they are erroneous. But have you ever seen anybody retract a negative statement? You just let it stand there.
You gotta have a lot of bravery. Thank
No,
you.
that's just not done.
Yeah.
So,
Did you or anyone else replicate that 1 cubic centimeter ignition
I haven't had the
experiment?
guts to do it. You know, you just don't do that sort of thing, do you?
We've done it.
You have done it, good. Well, I'm glad, I'm sure. The various people report.
Well, we did it the cheap way. My laboratory, and it makes a beautiful laboratory, is an old RV, recreation vehicle.
Yes.
You got electricity, sink and water, and if you have an
Even air
explosion, you
conditioning.
step in the shower. It's beautiful.
Well, I think to stay on schedule, it's now 9:20, so I'd like to thank Martin Fleischmann for his talk. And the second speaker today is by Ed Storms. He worked for many years at Los Alamos National Laboratory, and his title is The Present Status of Chemically Assisted Nuclear Reactions. So that's another title, word for this.
Much better, right? I'll get out of the way.
People trained in science believe that chemically assisted nuclear reactions, or AKA cold fusion, is impossible. Yet hundreds of scientists worldwide have seen anomalous effects. These effects include heat that should not be present in the environment, extra energy. It's included nuclear products of various kinds, both radioactive and non-radioactive, and it's included various emissions, neutrons, gamma. Yet, and then this conflict between belief and observation has polarized science, and it has interfered with the normal development of the field. Now, the skeptics would argue that our current understanding of nuclear interaction is adequate to explain what we're seeing, that such reactions at low temperatures are absolutely impossible, and that even if it should happen by some miracle, the amount of nuclear products and their proportion, the kinds of nuclear products, are not correct. And therefore, they conclude that the experimental results are based upon delusion, experimental error, and they're just simply wrong. The fact that they're very difficult to reproduce adds to their argument. Now, the people who believe that these reactions can occur argue back that we are looking at a different environment, that these reactions occur only in periodic solid lattices. And under those conditions, you have an entirely different environment than you have in a plasma, as on which the current theories are based. And that within this environment, you have the potential for various subtle reactions to take place, or subtle mechanisms to take place that can overcome the Coulomb barrier and that can dissipate the energy throughout the lattice. The believers also argue that the difficulty in replication is caused by the difficulty in producing this unique structure within the lattice. And in addition, there's a rich assortment of models that are being developed to explain what's going on. It isn't that we don't have the explanations. I mean, there's a very large number of them. And some of the people here have contributed to this. Well, I believe at this point in the history of the field that there's a sufficient amount of information available to make an objective evaluation of what is conceived. And I would like to make a stab at that today. I don't have time to go into it in great detail, and if you're a skeptic, I don't think I would change your mind. But what I would hope to do is excite your imagination and cause you to look into the field in more detail. There's a tremendous amount of information out there. There's over 2,000 papers that have been published in peer-reviewed journals, conference proceedings, reports. There's an enormous amount of information available. And I will pick and choose out of that, and everybody in the field would probably make a different choice, but you're stuck with mine. Now, the original work was based upon the electrolytic technique that Martin Fleischmann described very well. But there are 8 other techniques that have now been found to initiate the effects. And that's very reassuring, because you wouldn't think that nature would only make this happen under one condition. So that gives me a certain intuitive good feeling about the reality of the effect. I should point out that the various techniques have both a light water and a heavy water branch. They and the heavy water and the light water produce different nuclear products. Now, right there is a very interesting observation, because if this were caused by delusion and error, you would expect the same reaction whether it was light water or heavy water. I mean, why should the cell care if it's error? Furthermore, the heavy water system favors palladium. It's not the only element that is active, but it's very favorable, whereas a light water reaction favors nickel. Palladium is inert in light water, and nickel is inert in heavy water. So again, you'd have to ask, why should the system care what the cathode is made of if it's air? Well, let's go through this list. I only have time to talk about the first three, and we'll talk about it in some detail, but let me go on and just give you a very brief thumbnail description. Plasma discharge in a liquid. Here, a liquid is, has in it two electrodes, and an arc is caused to occur between those two electrodes under the surface of the liquid. This has been found to produce excess energy as well as various nuclear products. It's fairly reproducible, actually. It's being studied here in this country and also in Japan. Low discharge and low pressure gas. This was developed in Russia, and it also has been found to produce excess energy in nuclear products. Proton conduction in semiconductors. Here, you have a material that is capable of dissolving hydrogen to some degree, and when it's hot. And a current is caused to pass through it while it's in hydrogen. And that current causes the protons to move, or deuterons. And that motion sets in place a process that produces excess energy. Sudden decomposition of the hydride. Here, a piece of palladium is loaded completely with hydrogen, or deuterium in this case, and then it's heated in vacuum, and the gas suddenly comes out. This has been found to produce various nuclear products. External mechanical stress. Here, a loaded material, palladium, for example, is bent or otherwise caused to experience stress, and that is also found to produce nuclear products. And then finally, there's the biological systems, which, if you have found it difficult to follow the possibility of these being real, this will really test your ability to have an open mind. But again, there's increasing information done very, very well in Russia and in Japan, in addition to all of the work that has been done over the last 20 years in this that's been largely ignored, that is supporting the possibility of nuclear reactions occurring in biological systems. Well, let's look at first the electrolysis of liquids. And I will concentrate on the heavy water branch. The light water branch is interesting, but we don't have time to talk about it today. This is a plot of excess power versus the current applied to an electrolytic cell. And this shows all the data that was available before 1991. I'd like to make 3 points. First of all, you can see there's a fair number of points here. These were all available prior to 1991, prior to many of the books and reports that were written by the skeptics. And when the skeptic says that there wasn't very much information available to them, you can see that they were quite misinformed. Most of these are individual samples, some of them the same sample that were subjected to different currents, but most of them are separate individual samples. You'll notice also that low currents produce practically nothing, and you have to go to higher currents for an effect to occur. We'll see that in a little more detail on the next slide. And Martin Fleischmann showed similar behavior in his work. The third point is that all the data fall below an upper limit. And that upper limit has been maintained over the years, in fact. All the data, even subsequent to 1991, falls below this line. That's typical of a phenomena that is dependent upon the material. In other words, a certain fraction of the material is active, and a sample that falls on this line, all of the potential sites are active, whereas other material, only a fraction of those sites are active. And it depends on how lucky you are as to how active your particular sample will be, including being totally inactive. which most of them are. So let's look at this phenomenon in a little more detail. This shows a linear plot instead of a log plot of excess power versus current density. And instead of different samples, this is the same sample that was subjected to a different current density. And you see, first of all, there's a very clear onset to this effect. Now you'd have to ask yourself, well, why should error or whatever, delusion, care what current you applied? I mean, you'd think that the error would just go up from 0, but everyone who has measured this, and it doesn't matter whether what the shape of the sample is, whether it's a plate, whether it's a rod, a wire, it doesn't matter whether it's an isoparabolic calorimeter or a flow calorimeter, that pattern is seen in every single study. Again, you'd have to ask why that error should suddenly appear everywhere if it's random. Bush's data, this line right here is the line that was in the previous slide which shows the upper limit. That is obviously a very good sample. The sample of McCubri's down here is very low, and his calorimeter is very, very sensitive, and so that's very real. And when the scale is magnified, you can see the effect much better, and I'll show you that very shortly. But you can see the same effect throughout the experimental work. Second, this shows you that same effect, but it also shows the growth of the excess power. The excess power does not come instantaneously. It requires patience. And that's one of the features of this field, which is very frustrating. I mean, I, for one, don't have a lot of patience, and for some strange reason, I've gotten into a field that requires an enormous amount of it. But most people who get into this field don't realize that, and so they do turn their experiments off before they should. The point that Martin made. But here you see a sample that was subjected to different currents during different times during its charging history. And you see initially it's 0, and then as it's been charged for longer and longer periods of time, the power grows in. That is characteristic of this phenomenon. Everybody sees that, regardless of their calorimeter or the shape and size of their sample. Well, why should this be? Why should the current have any effect? Well, this is the reason. This is work done at SRI that Mike McCubri's group did. This is excess power versus composition. And you see that in order that at low compositions, there is no excess power. And as you go to higher and higher compositions, you get more and more excess power. An increased current improves the composition. Now you have to realize that this composition is not the composition of the nuclear active region. This is the average composition of the sample. The nuclear active region is in the surface, which is at a much higher composition, but it is proportional to the bulk composition. But nevertheless, there is this relationship, and the imposition of a higher and higher current produces a higher and higher excess power. Now, if this were error, why would there be that relationship? I mean, skeptics have to explain these phenomena, which are universal in all measurements. I mean, that's one of the criteria that science uses to judge reality, and that is that a number of people must do the same experiment, thus eliminating bias on the part of the individual, and they must see the same